welcome to our keynote lecture. It is my great pleasure and my honor to introduce Alberto Abadie, who is our speaker this morning or this afternoon, wherever you are. So Alberto needs no introduction, but let me try. He is a world-renowned econometrician and statistician and empirical microeconomist. He has broad disciplinary interest in econometrics, statistics, political science, economics, and more. His area of research spans a lot of topics in program evaluation, causal inference, statistics, and econometrics. You might know his contributions to instrumental variables, matching estimators, difference in difference designs, and you might also know him as the father of synthetic control designs, which are extremely well known and widely used across social, biomedical, and all other sciences. Alberto, it's a great pleasure to be with you today and to have you. Thank you so much for agreeing to give this lecture. A note for our audience that we will be taking questions during Alberto's talk in the Q&A box that you have in your Zoom webinar. So if you have any questions, you can type them in the Q&A box. Those I will read those and select some of those questions to be asked at the end of the talk. Alberto will go for between 40 and 45 minutes, and then at 35 minutes after the hour, we will stop and we'll have 10 minutes for questions. Alberto, the floor is yours. Thank you so much again.
Thank you so much, Rocío. Gracias, Rocío. It is a great pleasure to be here, in fact, and I so grateful to the organizers of this session and for inviting me, and more generally to the organizers of the conference. And I'm going to talk today about synthetic controls as an experimental design, and this is a joint work with Jin-Long Zhao, who a former student of mine, graduated last year. He's in Boston University right now. So as many of you know, synthetic controls are usually employed in the context of observational studies to estimate the effect of aggregate events or aggregate interventions. And these are interventions or events that happen at the level of some aggregate unit, like a city, a state, or a school district, or a country. Okay, and synthetic controls use like a convex combination or a weighted average of units that are not exposed to the intervention of interest to reproduce the counterfactual outcome that we will have observed for the treated unit in the absence of the intervention. So synthetic controls have become very popular in empirical research in economics, and I think part of the reason is because the transparency of the method, and also because of the interpretability of the results. But also I think that a big reason for that is that many of the interventions that we care about as economists, they do not happen, they are not deployed at the level of individuals, they are deployed at some aggregate level. Like if you think about laws, regulations, like public policies, typically in many cases they don't apply to particular individuals, but they pass at the level of a state, they pass at the level of country, or they are as I said before, they are implemented at the level of a school district. And synthetic controls are to a certain extent open the door to estimate the effects of this intervention. And the point of the talk today is something very similar is going to happen in experimental design. In experimental design, we are going to have a setting in which it will not be feasible, or it will not be legal, or it will not be effective to assign the treatment at the level of particular individuals at the micro level, and we will have to assign the treatment sometimes at a a relatively aggregate level. And the question is, what we do in that setting? We spent quite a lot of time and effort, and we were very successful in developing methods to estimate or methods experimental design methods that we can use in the cases in which we can assign the treatment or no treatment to large number of individuals. But what happens in the cases in which we have only a small number of aggregate units and we have to decide which ones are going to receive the treatment and which ones are not going to receive the treatment. And this is kind of the motivation for this paper. And to give a little bit more motivations, I'm going to start with a like a simple example of a potential application of these ideas. Okay, so here is the sample. Suppose that there is a ride-sharing company in the US and they want to assess what is the impact of a new compensation scheme with a higher incentives for drivers. Okay, like perhaps they say like perhaps we pay drivers better and perhaps they're going to work more. Perhaps that's going to be good for everybody. So they consult with the this company has like a business analytic unit, of course, all of them do, and they think about, oh, okay, so this is what we are going to do. We are going to do a randomized control trial or an A/B test where drivers in a city, like are going to be randomized into the new program with a better incentives or the status quo. Okay, so like after thinking about it for a while, they realized that this type of experiment is going to be problematic, and it's going to be problematic at least for two reasons. First, there is the issue of fairness. I mean, like in this experiment, you will be paying like different drivers, different amount of money for the same jobs. Okay, and like of course, like many people may object to this, and at the very least, it would be like a a serious peer problem. But even if they are willing and able to deal with that, there will be like also like a important issue of interference, right? If drivers that are in the active treatment arm and they have higher incentives, like a drive for longer hours, they are going to steal business from the drivers who are in the control arm of the experiment, and this is going to result in biased experimental estimates. So these people decide that they are not going to do that. They are not going to assign treatment at random to drivers in a city. But they very quickly recall what they learned as an econometricians, and they say, okay, but I know what is the usual solution for interference. When we have interference, it's like we're going to randomize the treatment across cities. We're not going to randomize the treatment within this city. We're going to randomize the treatment across city, and perhaps we are going to assign half of the cities that we have, let's say in the United States, to treatment, and half of the cities to control. Okay, and in principle, this could be like an effective design, except for it has some usually serious problems. The first one is like it could be very, very expensive. Okay, and it's something like this company will try to avoid, like trying to doing this type of experimental evaluation in which you are going to basically increase pay for half of the drivers in the country, like could be considered like something that they are not able to invest all that money into it if they don't have like a better evidence that is going to create some type of gain for them. Also, it could still raise like substantial equity concerns. I mean, you don't want to have the firm in which you have in the same country, like half of drivers like with a one compensation scheme and the other half of drivers with another compensation scheme, and this has been assigned at random. Again, like from the point of view of PR, this is not great at all. Okay. Third problem is that this type of experiment could create great disappointment among the drivers in the treated arm. That remember, these are half of drivers in the US. If the program is rolled back after experimentation. So like imagine that we do this experiment, we decided no, like the new compensation scheme is not a good idea. So we are going to, we are going to dial this down. Okay, and you have, basically like half of the drivers in the US getting like pay cuts. That's something that you may want to avoid. And finally, in some cases, like the number of cities that where the ride sharing company is operating could be too small for effective randomization. Like you may have like just a small number of cities to randomize across. Okay, so they decide that they are not going to do that. So the question is, what can they do? Okay, so like this is that what they come to their minds, like well, what if we implement this program, this new incentive pay, as we implement it in one city to all the drivers in a city, And we advertise it as a pilot program or as a demonstration directly. So as a demonstration, we're going to go to the city, like change the the compensation scheme and see what happens. Okay, and so this is something that they could think about doing, but then there are all kind of questions that that this is going to open, like which city or cities should be treated. That's the first question. I mean, like they have many cities in the country. Which one are they going to choose? In which cities or cities should be used as a comparison or control? It's not clear that once you have chosen like 2 or 3 cities, or one, the rest of them should be the comparison. Perhaps you can select from there a better comparison than just all the rest of them. And the first thing that they realize, of course, is that this is a setting when randomization of the treatment is going to create defective designs, right? Like ex ante, if you think about this, what's going to happen here, ex ante, randomization is going to produce bias estimators, okay? Like if you're going to choose one city, all the cities have to, kind of the same probability of being chosen, let's say, this will produce some type of bias estimator. But the problem is that the estimator exposed is going to be severely biased if the city that you happen to choose at random, the city that you choose at random happens to be, non-representative of the entire set of cities that you have in mind. And, then the treated cities and the control cities are going to be very different in their characteristics. Okay. So this is, they may want to do this, but still they don't know exactly how to do it. I mean, they have all these choices to make, these 2 choices, and something that they have realized, almost immediately is that while randomization again is giving them something that is unbiased ex ante, is really a good idea because exposed could be severely biased. Okay, so this is kind of the motivation. So to address this type of questions, what we are going to do in this paper, we are going to employ the synthetic control method, but instead of employing the synthetic control method as an observational design, research design, we are going to employ it as an experimental research design. And we are going to employ it to select the treated units in non-randomized experiments. Okay, this will be an experiment in the sense that the experimenter is going to have control over the intervention, but it's not going to randomize intervention because of the problem that randomization creates that we discussed in the previous slide. Okay, so we are going to choose we are going to use synthetic controls to select treated units, and also to select the untreated units that will be used as a comparison group. Okay, and this type of designs we are going to call in this paper, synthetic control designs to refer to the resulting experimental designs that we are going to produce. Okay, and the choice of the treated unit in this setting, we will try to accomplish two objectives. The first one is that the features of the treated unit should be representative of the features of some aggregate of interest, like the entire country. We shouldn't, choose a unit that is not very representative of, of the characteristics of the entire country. If you are, interested in what is the effect of this treatment on the entire market. Okay. The second goal that may not be in tension with the first one, but is also a separate goal, is that the treated unit should not be idiosyncratic in the sense that their features cannot be closely approximated by the units in the control arm. I mean, you don't want to choose a unit as a treated unit that you are going to give the treatment to this treated unit, but you need to reproduce somehow the counterfactual of what would be the outcome for this treated unit in the absolute treatment. And if this unit cannot be approximated by other units in your sample, you may not want to use that particular treated unit. So that's kind of the idea. So perhaps you have already noticed, but here, in contrast to the observational case, to the case of observational study, we are going to have not one synthetic control unit. We are going to have 2 synthetic control units. We're going to have a synthetic treated unit and a synthetic untreated unit. Okay, in the usual observational setting, like the treated unit is given to us, we don't have any power to decide which unit is going to be treated, and all our inferential procedure is about how to choose an untreated unit that is going to be a good comparison, and how to estimate this treatment effect by comparing these 2 units. here we have the power of choosing like the treated unit, and we have the power of choosing the an untreated unit, and we are going to have two synthetic units, one that is treated and one that is untreated. So, and this is, I have to say that this is related to work that the people are currently doing at Google, Uber, and other places. And something that I want to point out is that currently like synthetic control are widely used not only as observational designs, but to some extent that they also experimental designs in the tech industry to evaluate the effects of potential interventions. Okay, so let me try to give a little bit of a conceptual framework and formalize the nature of the problem and our approach to it. We're going to be in a setting in which we have T time periods and J units. Like the J units could be cities in the ride sharing company example, and the T time periods we're going to divide into two. Like we'll have like a T0 pre-experimental periods and T1 post-experimental periods. So like the first T0 periods is before experiment, and using information available at T0. We aim to select the set of units that will be administered treatment during the experimental period. So like we're sitting at T0, we're going to choose the units that will be treated in T0 plus 1, T0 plus 2, all the way to T. Okay, and this is going to be a setting of potential outcomes. We are going to have the potential outcome with intervention for unit J at time T, and the potential outcome with no intervention also for unit J at time T. And the treatment effect we are going to define as usual as the difference between these two potential outcomes, and we are going to define treatment effects for each unit in our sample, but only for the post-experimental periods. Okay, and of course, as you can imagine, in the post-experimental period, we are going to observe an outcome, and this outcome is going to be the outcome with the treatment for the treated unit, and it's going to be the outcome without the treatment for the non-treated units, and that's the reason why we cannot observe this difference directly. We will observe the outcome with the treatment for the treated and the outcome without the treatment for non-treated, and that's why we want to establish some comparison that seems reasonable to reproduce the counterfactual that we don't observe, the counterfactual outcome that we don't observe. Okay, so what are we trying to estimate? We are going to talk about a couple of parameters that we may try to estimate, but the first one that comes to mind is some type of average treatment effect. It's it's going to be the average of the treatment effects for all the units in our sample, and we are going to use some weights that we know about. This could be like 1/J if you are just taking the simple average, but you may have some other known weights that perhaps they are based on the share of the population in the city as the share relative to the total population. Okay, and the experimenter in this design is going to choose two vectors of weights. It's going to choose like a W, and it's going to choose V. Okay, and those are going to be vectors of proper weights. They are going to be non-negative, and they are going to sum to 1. But also they are going to the product of the weights for the same units are going to be equal to 0. So if W is positive, that means that V is equal to 0, and the other way around. Okay, so that's the weights that we are going to choose. And what is the meaning of those weights? Okay, so the units, once we choose the weights, like the units with W bigger than 0 are units that we will assign to the intervention of interest, okay, in the post-intervention periods. And the units with W equal to 0, these are the ones that are not going to be treated, and they are going to constitute an untreated reservoir of control units that we are going to call a donor pool. And among all these units, all the units with W equal to 0 that we are not treating, we're going to choose some units that we are going to use to estimate the average outcome under no intervention, and those will be the units with a V weight bigger than 0. Okay, and our synthetic control estimator is going to be very simple. It's going to be the synthetic treated unit, the outcome for the synthetic treated unit minus the outcome of the synthetic untreated unit. Okay, where these y's are the observed outcomes, and the weights are the weights that we are going to choose. Okay, so that's the way that we are going to define the estimator. In the observational case, the difference between this and the observational case is in the observational case we don't have this part. We just have, like the outcome of the treated unit that usually is the first unit. So this will be equal to that is is affected by the intervention of interest. So in the observational case, we don't choose which unit is going to be treated. In the experimental case, we're going to choose which unit is going to be treated. Okay, so if you are going to play in this framework, we can think about, what are going to be the goals of the experimenter. Okay, so the first goal of the experimenter is to choose a synthetic treated unit that reproduce the outcome under the treatment for the population of interest. Okay, this is something that you may want, to have the treated that are representative in their outcomes of the outcomes that you observe if the entire population is treated. Okay, and the second goal of the experimenter could be do the same with the V's for the non-treated outcomes, so choose a synthetic untreated unit that is going to reproduce the outcome under no intervention for the entire population. Or alternatively, you could say, okay, instead of trying to reproduce the entire population, I will try to reproduce the treated. So what I'm going to do is I'm going to choose a vector of weights that is going to reproduce the outcomes that you would observe for the treated under no intervention, and those treated are weighted by their weights, like W. Okay. So so we have these three, this is 1, this is 2, and this is 3. Okay. So if 1 and 2 holds, then the synthetic control that you have put together is going to exactly reproduce the average treatment effect in the population. If instead 3 holds, the synthetic control design, what it's going to give you is the average effect of the treatment untreated, weighted by the W's that you are producing for the treated. Okay. So this would be something excellent to do if we could. The problem is that we cannot directly fit potential outcomes because we don't observe these potential outcomes in practice. So what are we going to do that? How are we going to do that? So instead of fitting the potential outcomes directly that we cannot observe, we are going to fit the predictors of these potential outcomes. So that's the idea behind synthetic controls. So we are going to define a set of estimation periods that are a subset of the pre-intervention period. You will see there were some periods, we will reserve some periods that belong to the pre-intervention periods that we are not going to use for estimation, and we will use them later for inference. So, but in principle, we will have a bunch of periods in the pre-intervention period that we will use for estimation, and we are going to use the outcomes that you observe for each of the units in these pre-intervention periods, and you are going to define your predictors of the potential outcome, without the treatments, the previous outcome, pre-intervention outcomes, and other treatment covariates aside from the outcomes that are good predictors of the outcomes of interest. Okay, and what we will try to do is we will try to match values of the predictors. And the first thing that it comes to mind, when you think about how to do that, well, perhaps the first thing that we can do is match the average values of the predictors. We want perhaps synthetic treated unit that is matching the average outcome, the average values of these predictors in the population of interest. So the first and most basic synthetic control design, solves an optimization problem that is represented here in this slide. What you are going to do is okay, you are going to choose weights, W and V that fit the characteristics of the predictors or the values of the predictors in the population. Both for the treated and for the both for the treated units and also for the unit that serves to reproduce the counterfactual without the treatment. So again, we will try to minimize these discrepancies, and these are going to be, as I said before, positive weights that sum to 1, that the product is equal to 0, and we are adding here an extra constraint, and that that you may want to add if you want, that that is putting a restriction on the minimum and maximum value of a treated unit. So for budgetary constraints, you may be able to only treat 1 or 2 or 3 of the units, and that is something that is and this is reflected in this restriction. And instead of using a restriction of the number, of course, you could use a restriction based on the budget. If you know how much it's going to cost, treating each unit, you could have a linear restriction that tells you which units you can effectively treat given your budget. But it's it's not in this slide. Okay, so this will be the basic a synthetic control design for experimental study. And if you go to the paper, in the paper, what we do is we start with this, and then we develop this in in several directions. Okay, for example, you can show that these synthetic controls that they minimize this objective function they are not necessarily unique. And we are going to propose ways in which we're going to choose among all of them, all possible solution in case that the solution is not unique. So there are many variations of this basic theme, but one that I want to talk about two basically. One is okay, you could choose the treated unit to reproduce the characteristics of the population, and instead of choosing the untreated unit to also to reflect the characteristic of the population, you can choose the untreated unit to reproduce the characteristics of the treated. So basically, for each treated unit, you are going to construct a synthetic control, and you are going to aggregate them, in order to try to estimate what would be the counterfactual outcome with the treatment for the units that were treated. Okay, and this parameter here basically is trading off this discrepancy and the discrepancy over here. Okay, so that's another way to approach this design. Finally, something that we may have into account is that we may want to construct these synthetic controls, but without considering the entire sample as a whole. And here we have the reason why, in these two panels, panel A and and panel B, we have exactly the same units. Imagine that these are the predictors, and it's a very simple setting in which it's two-dimensional. So we have predictors in 2 dimensions, and we're trying to choose which of these units, that each of these units is represented by one of these points, is going to be chosen for treatment. Okay, and if you treat the entire population, or if you do this for the entire population in one step, you may choose a unit like this. The units in red will be the treated units, the one that are closer in some way to the population average. Okay. The problem is that these 3 treated units are, very good, representing the characteristics of the units that are over here, but they are not that good representing the characteristics of the units in this cluster or the units in that cluster, right? So, one easy solution for this is to divide the population in these 3 clusters, 1, 2, and 3, and estimate a different treated and different untreated synthetic units within each of the clusters. And if you try to do this if you try to write as an optimization problem, you can do it. It's messy, and of course, in practice, you will never try to solve this. You will first, do the clustering of the units, and then you will solve it cluster by cluster. Otherwise, it's going to be a computational nightmare. Okay, very good. Okay, so now the question is and what are the properties of the these estimators anyway. And this may sound like a reasonable way to try to get the treated to represent the population, and try to get the untreated to represent the population or to represent the treated. But do we have any guarantees about how well or how bad these estimators are going to behave? And for that, what we are going to do is something that people do in the synthetic control literature quite a lot. We are going to adopt a benchmark model for the data generating process, and in this case, it's going to be like a linear factor model. A linear factor model is something that is very popular in the synthetic control literature because it's a little bit more general than, or I would say like much more general than the the difference in difference type of model. And the difference in difference type of model, all units are the same except for one shift, okay, that doesn't change in time. So that will be the case in which let's say that this doesn't exist. Okay, this says all potential outcomes are basically the same. They follow the same process except for you have a unit fixed effects. Okay, and so in this is kind of different settings in which the treated and non-treated follow the same trajectories in time. The nice thing about the linear factor model, it allows you to have treated and non-treated following different trajectories, and still you can get some type of results as long as you have some a factor structure in the compounding part of the equations where you cannot observe these characteristics, these fixed effects. Okay, so in any case, these are going to be factor models for the potential outcome without the treatment, the potential outcome with the treatment. They are going to depend on characteristics that we observe. Remember, these are the characteristics that we observe, and they are going to depend also on these factor loadings that we don't observe. Okay, and both the characteristics that we observe and the one that we don't observe are going to be multiplied by coefficients that change in time arbitrarily. Okay, and these guys here, these are going to be random shocks. Okay, so in the I should say this, by the way, before I forget. In the literature on synthetic controls in observational study, you will not see this equation. This equation does not appear, only the first one. And the reason is we don't need to assume anything. We don't need to assume anything about the outcome for the treated unit with the treatment. We observe that one. That one we can write it down and put it in a drawer. And now all our inferential effort is estimating the potential outcome without the treatment for the treated unit. Okay, but here we are in a very different setting because we have to choose the treated and we have to choose the untreated in a way that they match their characteristics in some way, and not only a observed characteristic, but hopefully some an observed characteristic. So that's why we're going to observe this or assume this linear factor model for both potential outcome with the treatment and potential outcome without the treatment. Okay, so assume that you have this linear factor model. Assume that we can match the characteristics in the population with the a synthetic treated weights, and also with the synthetic control weights. We can match all these characteristics with probability 1. And then under some assumptions that I'm going to leave in the background, and under some regulated conditions, you can show or you can establish a bound on the bias of the synthetic control estimator. And basically this is a finite sample bound and tells you that this is going to depend on the number of pretreatment periods that you're considering for estimation. And there is a constant here that is long and messy, and I'm not going to talk about in detail, but the only thing that I want to say about this constant is it's going to depend crucially on the variance of these transitory shocks. So if the variance is large, we are going to, we may have a setting in which we are prone to overfitting, and we're going to have bias. If the variance is small, the variance will be small. Okay, so this is in fact a result that is very, very much or is very, very similar to the result that we obtain for synthetic control estimators in observational studies. What about inference? So we can try to do some inference in this setting, and remember that we have these factor models for the outcomes without the treatment, and also factor models for the same factor models but with different coefficients for different transitory shocks for the outcome with the treatment. And what is going to be the null hypothesis that we are going to consider here? Well, the null hypothesis that we are going to consider here is the following. Let me try to erase this. Is this that basically, these two coefficients, these are the same. Okay, and these two have the same distribution. They are not the same, but they have the same distribution. Okay, so that means that the potential outcome with the treatment and the potential outcome with the treatment, they have the same distribution. This is going to be a null hypothesis. It's basically a hypothesis of no effect. Okay, and this is the hypothesis that we're going to test. And how are we going to do that? Now we are going to use the pre-intervention periods that I then use for estimation, what we are going to call the blank periods. Okay, these are pre-intervention periods which we observe pre-intervention outcomes, but they have not been used to calculate W star or V star. Okay, and for this pre-intervention period, you could estimate what you could call placebo treatment effects. You could estimate treatment effects, in the periods before the intervention, like using the W's and the V's that we have estimated before, but now we apply it to pre-intervention period that we have not used for estimation. Okay, so you're going to have like a bunch of estimates here. One, you are going to have all this placebo effect for the blank periods, and you are going to have treatment effects for the post-intervention periods, and we're going to put in all of them. We're going to put all of them in a vector. Okay, and what we are going to do for inference, this is basically going to be permutation inference. We are going to, under some conditions, again, I'm going to keep this in the background. These things are going to be exchangeable, and we are going to, take combinations of we're going to take combinations of the T1 units, the number of post-intervention period, among all this vector. That this vector, the size of this vector is T1 plus the number of blank periods, and we are going to construct vectors of these combinations. Okay, and our test statistics for each of the vectors is you can choose different test statistics, but here I'm going to take the average of the absolute value of the elements of the vector. Okay, and our the way that we are going to construct the test, the p-value is basically going to see in which cases each of these combinations, it's going to look at how many of these combinations that we can take at random produce values of the test statistics that are larger, or I should say not smaller, than the value that we obtain for the E hat. Like this E hat is the one that the one. Do I have this? Sorry, I don't have this defined, but this E hat is the one. Oh no, it's here. Sorry, there you go. This E hat is the one that contains only the values of the post-intervention treatment effects. Okay, so this is the way that this test is going to work. Like people call this permutation test or conformal inference, and it's basically based on some notion of exchangeability of the exchangeability of the components of this vector. And so, what are the properties of this test? So this is what we have. Basically, what this tells you is that this test is going to give you close to correct size with a hopefully with high probability in when the number of estimation periods is large, and this is a finite sample result. This is not an asymptotic result. I have to say, however, just to be clear about this, that at this point this result is a little bit aspirational, because yes, we do have the result, but the C is quite large, and we have there are ways to reduce the value of C, the value of this constant, that are quite you can do it quite trivially, but we're trying to think about how far we can go, reducing this constant. Okay, very good. So these are I went through the what is the synthetic control design. I went through the what are the properties of this type of estimator, and what I want to do now is to go to a little bit of a simulation results, and then I will conclude. Okay, so we are going to have this paper is right out of the oven. So like our simulation is like a, relatively small, and it's something that we'll have to do a little bit more of this. But here is the setting. We're going to have like 15 units, like 7 observable covariates, 11 unobservable covariates, 30 periods in total. We have 25 pre-intervention periods and 5 experimental periods. We are going to compute the weight using the first 20 pre-intervention periods, and we are going to leave the last 5 pre-experimental periods as planned periods to do inference. Okay, and then you have some details on the data enabling process. And what we have here is this is a result for one random simulation. I think the first one that we get, right? Is what you can see here is like for the pre-intervention period. Sorry, no, that's not the pre-intervention period. This is the pre-intervention period. Okay, and these are the estimation periods here, and these are the blank periods. And here, at the end, we have the experimental periods or the post-intervention periods. Okay, so in this part, on all this part, we fit the model. Okay, this part here, we use for inference, and this part here we use to get we use for inference also to get our point estimates. Okay, and so this is the type of result that we get, because in the simulation we use a different values for the parameters of the linear factor models and the treatment and the non-treatment. There is some effect that emerges after after intervention when you observe yi instead of yn for the treated, and this is our estimate of that. Okay, and when you look at the difference between these two curves, the two curves that I have in the previous slide, the difference is very small during the estimation periods, very small during blank periods, but quite large during the experimental period. And in this case, the p-value is is quite small. Okay, we will react that the process for yi and the process for yn are the same. Okay, but of course, this is only one simulation. And you may be curious to see what happens when you do many of them, and we have results for that, right? And what we're going to do is what I'm going to show you for this research design. So we're going to have, for each time we run the simulation, we're going to have different values of the parameters. Okay, and what I have here is the average of the different values of the true parameters over the 1,000 simulations, that they go from minus 13 in the first post-experimental period to basically -2 in the last post-experimental period. So these are the two parameters. I should say the average of the two parameters that we're trying to estimate, and we average them across all the simulations. And these are what I show you here is these are the average of the estimates. And as you can see in this, at least for the simulation with this data engineering process, that is I have to say still quite favorable for what we want to do. We obtain a very precise results in terms of estimating the treatment, not only on average, but also as in terms of a mean absolute error. And something that you can see is the mean absolute error of our estimate goes down as you allow more and more units to be treated. So this is then constraint case in which you say, I am able and willing to treat as many units as the algorithm tells me. And this is the constraint case in which you say, well, perhaps I can only treat 1 unit, or perhaps I can only treat maximum of 2 units, or maximum of 3, or maximum of 4, and so on. And you can see how, if you allow yourself to treat more and more units, the mean absolute error goes down, but it's still relatively low for for the constraint case, even if m bar is not very large. And by the way, you will notice that this row, it's this row, and the reason is basically 7 units is this time constraint result. Okay, so I think that I am more or less at the time where Rocío told me to stop. So I have some conclusions. So let me just read them more or less. in the past, like experimental design methods have been concerned with setting which we have like a large sample. And, we are going to have like many units that will be in the treatment group and many units will be in the control group. And of course, as you know, this has been like a super successful, super useful, like a research design. And we employed for many things in economics and, has clarified like a lot of questions that we have in mind. However, it, it shouldn't be the only game in town. Like it clearly becomes inadequate when you can only treat one unit or two units, small number of units, perhaps because you have to deploy your treatment at some aggregate level. So like the idea here then has been to apply synthetic control methods that we use in observational study, to apply them to experiments, to cases when we can only treat a small number of units. And this synthetic control design is going to optimize only over the identities of which one are going to be treated, which ones are going to be untreated, and also over the weights that we are going to assign to them to reproduce the counterfactor of interest. In corporate research and also in academic research, we are often in cases where interventions that we would like to make, but we cannot do it at the level of the micro units, perhaps customers or workers or family, because like I say, it's unfeasible, unethical, impractical, ineffective, or you go to jail. And so therefore, there are many cases in which there is quite a lot of potential applications for experimental settings when you assign your treatment at the level of a large aggregate unit. Okay, thank you. I think I am more or less at the time mark.
Actually, quite literally 35 after the hour. Thank you, Alberto.
Thank you.
This is such interesting work. Thank you so much.
Sure.
I'm going to encourage people to continue submitting questions. We have exactly 10 minutes to discuss some of these questions. So the first one, Alberto, from Henry Alexander Ballesteros Quiroga, asking, what are the main challenges in terms of identification and estimation in synthetic control strategies that need more theoretical work in the near future?
That's a good question.
Yeah.
Yes. So there are many challenges. Like, for example, one of the things that we have here is for my first result in terms of bias of the synthetic control estimator, I have assumed that I can reproduce the characteristics that I want to reproduce exactly with probability 1. And that means, and I always try to emphasize this, the synthetic control method is not generic in the sense that you can apply to anything, right? You can apply it when you have good comparisons, and you may not want to apply it when you don't have good comparisons. It's very much like difference in different estimators. Sometimes work, sometimes don't work, right? But when they work, they give you quite a lot of credibility. And for example, that would be one area in which I think we need more work, what happens with synthetic control estimators when we cannot exactly reproduce the characteristics of the treated unit in the observational studies or the population of interest in experimental studies. And there is some work done by Bruno Ferman, but I think that it is kind of an open area in many respects. Inference is also an open area in many respects. I mean, Rocío and Matthias and Jinju, they have done very nice work on talking about or designing confidence intervals for synthetic control estimators. There are different ways in which people do inference in this setting, and it's still of an open question in which cases you should apply what exactly. This type of conformal inference that I was talking about today, the type of inference that Rocío is talking about in her paper, or the type of inference that we have in other papers that is kind of more, a permutation, randomization type of inference across units. And it's a little bit unclear to me what is best in each context and in each scenario. So these are a couple of things that I have in mind. But then, like everything that you can think about with estimation, like robustness, sensitivity, mediation analysis, like all of that. I mean, there is so much work to do in this, for this type of settings, and yeah, quite an open feeling for us.
It is. I think people are going to be working for a long time. I am waiting to see if more questions are submitted, but I can ask you a question in the meantime, Alberto.
Sure.
So have you, but I'll stop immediately if I see a question coming, because I want to give people the chance. I encourage everybody. I think there's a lot of people attending, but not a lot of people asking questions. Have you done this procedure by first selecting the treated unit or the synthetic treated unit that you want to treat, and then maybe forgetting about that first step and then running synthetic control as if that were your unit?
Yes, you could do that. What we do it in one step, right? We select the treated and the untreated in one step, and like again, like the problem in doing just, I'm just going to select the treated and then I will worry about the comparison group, the control group, is that you may end up, I mean, may or may not, but you may end up with a treated unit that, yes, reproduces the characteristics of the population, but it's not easy to reproduce. Like you can think about the samples in which you have many units here, and one unit there, right? And like, or 2 units there, and you will take these 2, but perhaps you want to take 2 here and 2 here, or or 2 here, 2 here, and 1 here. I don't know, something like that, right? Yeah. So that's why we try to think about, like selecting these groups, like at the same time instead of doing it instead of doing sequentially.
Yeah, this makes sense. Yeah, this makes sense. The need for doing it simultaneously. I have a question from Carolina Suarez, Ulloa Suarez. The question is whether the results would be affected if we have a larger post-intervention period, since a lot of things can happen after the intervention that affect the outcome variable. So in other words, when do you stop? When do you stop?
You stop when you think you should stop. I mean, like this is a great question, but it is there is no, I mean, there is not much that you can do with the statistics about this. I mean, like that, a great deal of it, what you have to do in empirical research is based on your knowledge of the details of the problem and what type of what type of which other events or interventions may affect the outcomes of units. And not only that, sometimes like we have to go ex ante and discard units from the study because today we know that they were affected by like something like a different, right? And that they would be very difficult to like reproduce with other units. I don't know, like let's say that you're doing the study with the drivers, and there is a unit in which have like a great floods of the water, like cars were not operating there. Like you will take that out of your sample, and there is not much in the like you can try to look in the data, where you have anomalies, but like in many cases we just have to use our knowledge of the problem to see how far is far and how how different is different. And but also like you have the same type of events, like okay, so let me put it this way. There are some modes of inference in which if you have the same type of events, like other events that are affecting like not only the treated unit but also like some other units, control units, that will make your like a so to speak, confidence intervals very large, right? Because like this will be the type of inference that you do when you permute the treatment across units. And if like you have like some shocks that is happening after the intervention period that affects the outcome of the units, and those accumulating times, you're going to see that like those are going to register as a treatment effects for the placebo units, and you will have like large confidence intervals, so to speak. I'm being a little bit informal when I say confidence interval.
Maybe we have time for one more. Freddie Pinson, do you see possible to use synthetic control strategies to estimate the impact of free trade agreements, and what could be the limitations?
Trade agreements?
Mm-hmm. This is very
sure,
specific.
Why not? Why not? But the thing is that I'm not a trade economist. This is very much related to the previous question. In fact, there is some theorem there that says that you cannot estimate causal effects without background knowledge, and because you can estimate what is characteristics of Y, what are characteristics of the the distribution of the treatment. You can estimate many things, but the causal model is something that you put on top of that at the end, to some extent. Like you can put it also at the beginning in some cases, but it's kind of like a added knowledge that you put on top of that. It's like when you say, okay, I'm going to have like a comparison of means. This comparison of means is not clearly, may not be a causal effect, but if I have the extra knowledge, but that was created by randomization across many units, then I'm going to interpret this way, right? So you know something about how the data were generated that it may not be like may not be obvious just from looking at the data, and this is kind of the same. I mean, like, can you estimate this, or can you use synthetic controls to estimate the effect of trade agreements? I would say yes, depending on the setting and depending on which are the treated unit, depending on whether we have good comparisons for the treated units, and like how much noise we have in the data. You remember like when we were in this slide here. Let me try to go back here. Here, this slide here, we say like crucially, like the noise that you have in your outcome variable is going to show up there. So you have a lot of noise, you may have a lot of bias. So these are kind of settings where these are kind of things that you have to evaluate setting by setting. I have a couple of papers. One is in the Journal of Economic Literature. Another one you can find it on my webpage. Is called Synthetic Control in Action, that tries to describe under which conditions you can apply synthetic controls and under which conditions you should not apply synthetic controls. And perhaps it is useful for you to read those papers and see those conditions applied to the type of empirical setting that you have in mind. But from me, like a Shante, it's very difficult to say they will or not. I hope this helps.
Thank you, Alberto. I think that's very helpful. That's a great point. Alberto has an amazing article that is 2021, no? That is really a very recent take on the literature on synthetic controls that takes you from the very beginning to where we are now. So I recommend that article to everybody who wants to learn more about synthetic controls. I think we are 2 minutes officially past the time that we're supposed to end. I thank everybody. I thank you, Alberto, in the first place, from taking time in your busy MIT professor life and give us 1 hour of your wisdom. I thank the audience for joining us, and I encourage everybody to come to the other sessions later in the day and tomorrow.
Thank you, Rocío, and thank you, Juan, and all the attendants and organizers. Bye.